You know, you walk down the street on any given Tuesday, feeling the pavement under your shoes, and you probably assume you are walking on solid ground.
Oh, absolutely. Yeah, everyone does.
Right. You assume the earth beneath you is just, I don't know, compacted dirt and rock holding up the world. But if you could strip away the top few layers of our modern cities, if you could somehow x-ray the dirt beneath our feet, you wouldn't see solid earth at all. You would see this hidden subterranean forest.
It is, it really is an incredible image to wrap your head around. I mean, millions upon millions of massive columns made of concrete, steel, and timber plunging deep into the dark.
Yeah.
They are essentially the invisible legs for almost everything we build.
And without this hidden forest, our entire modern world, like the suspension bridges, the skyscrapers, the coastal highways, would literally just sink into the mud under its own weight.
Just sink right in, yeah.
So today, we are going on a deep dive into the subterranean engineering that keeps our civilization afloat. We are talking about piling.
Yes, a massive topic.
Totally. And to guide us through this underground world, we have two sources on the desk today. First, an in-depth engineering article from Tensar that really breaks down the brute force physics of pile foundations. And second, we have our hands on an official, highly detailed project specification document for piling works.
The spec document, right.
Yeah, it's simply titled Document S1.2 Revision 01, which sounds dry, but it's actually wild.
It really is, because it brings a completely different perspective to the table.
Uh-huh.
I mean, we aren't just looking at the theory of how you drive a steel pipe into the mud.
Right.
That specification document reveals the strict, almost obsessive rules and legal frameworks that govern how we are actually allowed to manipulate the earth.
It's intense.
It's a masterclass in extreme risk management. Because, dealing with 180-ton machinery, that can easily cause a huge catastrophe if the math is even slightly wrong.
Okay, let's unpack this. Because before we get into the 180-ton rigs and laser-guided drilling and all that, we have to look at why we even started shoving giant columns into the dirt in the first place.
Right. The origin story.
Yeah, the fundamental human problem that necessitated piling is actually as old as civilization itself. Basically, we just really love water.
We do. I mean, early civilizations wanted to live near rivers for trade, for communication, and obviously for agriculture.
Yeah.
But the land near water is invariably swampy, it's silty, and it is structurally very weak.
Super weak.
So if you build a heavy stone structure on a riverbank, it just sinks.
Right. And the engineering article actually mentions the Swiss river dwellers using timber piles to elevate their homes against floods like 6,000 years ago.
Wow, yeah.
And the Romans were driving timber piles into the riverbed in London and Corbridge over 2,000 years ago just to build bridges.
What's fascinating here is that the core engineering principles from millennia ago remain fundamentally unchanged.
Like the physics are the exact same.
Exactly the same. We just use,
Yeah.
Heavily reinforced concrete and massive diesel hammers today instead of wooden mallets. But the entire goal of piling is load transfer.
Load transfer, okay.
You are taking the crushing weight of a structure above ground, bypassing the weak, compressible soil just below the surface, and transferring that load down to stiffer, less compressible soil or rock much deeper down.
Let's clarify a quick definition from the sources before we really get into the physics, because I know the terminology can get a bit muddy here.
Oh, sure.
There's a big distinction between a pile and a pile foundation.
Right.
The pile is just the individual cylinder, right? Like the single column of concrete or steel. But the pile foundation is the entire system, the whole series of these columns acting together as the base of the structure.
That's right. And the way those individual piles transfer the crushing load of a building generally falls into two distinct physical categories. You have end-bearing piles and friction piles.
Okay, so imagine you're standing in a swamp. If you take a really long wooden stick and push it straight down through the soft mud until it finally hits a solid layer of bedrock at the bottom and it just can't go any further, that's an end-bearing pile, right?
Perfect analogy, yes.
So the weight resting on top of the stick goes straight down the shaft and rests entirely on that deep, hard rock. The mud around it isn't really doing any of the lifting at all.
Exactly. The load completely bypasses the weak soil. But friction piles operate on a completely different mechanical principle.
Okay, so for a friction pile, imagine you take a really rough, textured stick and you shove it into a deep bucket of incredibly dense sand.
Uh-huh.
Even if the stick never actually hits the bottom of the bucket, you can push down on the top of the stick with a massive amount of force and it won't move.
Right, because of the grip.
Exactly. It's held in place entirely by the grip. The friction of the sand squeezing the sides of the stick along its entire length.
Yeah, to put some actual physics to your analogy, what you were describing is lateral earth pressure.
Lateral earth pressure.
Right, so the sheer weight and density of the surrounding soil squeezes inward against the enormous surface area of the pile. In a friction pile, the load of the skyscraper isn't going straight down to a rock at all.
It's radiating out.
Yes, it's being transferred outward, radiating into the surrounding soil. And depending on the specific geological makeup of a site, engineers might rely entirely on end bearing, entirely on friction, or sometimes a combination of both.
So now that we understand the physics of why we need these columns, we have to look at how we actually get them into the earth.
Which is where it gets complicated.
Yeah, because reading through the engineering breakdown, there is a massive divide in construction philosophy here.
Massive.
You basically have two choices. You either drive the pile into the ground with brute force, or you bore a hole for it. Let's look at driven piles first.
Driven piles are preformed off-site. So a factory manufactures a square precast concrete column, or maybe a heavy tubular steel pipe.
Okay.
It's brought to the site, stood perfectly upright, and then a massive percussion hammer repeatedly slams it into the ground.
Just a huge diesel-powered hammer dropping thousands of pounds of force over and over again.
Over and over.
And the article points out a really crucial side effect of this brute force, because when you hammer a solid object into the earth, the soil doesn't just magically disappear.
No, it has nowhere to go but sideways.
Right, it gets violently shoved sideways.
It displaces an equal volume of earth. And this lateral displacement is highly beneficial in granular soils, like loose sand or gravel.
Why is that good?
Well, as the pile forces its way down, it actively compacts the zone of soil immediately around it. It essentially squeezes the earth, increasing its density.
Oh, wow.
Yeah, so the pile makes the ground around it stronger just by being forced into it, which vastly increases that friction grip we just talked about.
But the text is very specific about a major limitation here, right? This compaction only works if the poor water pressures in the soil can dissipate rapidly.
This is a critical point of failure in geotechnical engineering. You see, soil isn't just dirt. It's a matrix of solid particles with microscopic spaces between them, and those spaces are very often filled with water.
Right, poor water.
Exactly. So if you drop a massive hammer onto a pile in saturated, silty soil where the water can't drain away quickly, the force of the impact transfers directly into that trapped water.
The water takes the hit instead of the dirt.
Yes. The pressure of the trapped water violently spikes, pushing the actual soil particles apart. And in an instant, the soil loses all its shear strength and shear resistance.
It just fails.
It undergoes liquefaction. For a brief moment, the solid ground literally behaves like a heavy liquid. And, well, you can't build a foundation on liquid.
Wait, on top of the soil turning to liquid, driving piles creates massive seismic vibrations too, right?
Oh, absolutely.
You are basically generating a localized earthquake every time that hammer drops. So if you are building a new tower in a dense urban environment right next to a historic building or, I don't know, a subway line, the vibrations from a percussion hammer could literally shake the neighboring foundations apart.
They really could, yes.
So if hammering these things creates a mini earthquake and requires perfect drainage so the ground doesn't turn to soup, why don't we just bore every pile? Isn't pouring concrete on site always better? Boring a hole seems infinitely safer and less disruptive.
Well, boring a hole is certainly less disruptive to the neighbors, but it introduces immense logistical complexity.
How so?
Think about it. Driven piles are fast, and crucially, they are quality checked in a factory before they even arrive. You know the concrete is perfect.
All right, no surprises.
But with a bored pile, which is also known as a replacement pile, you are removing earth and casting concrete in a blind hole deep underground. You are essentially building the foundation in the dark.
And the ground desperately wants to collapse in on that hole. The article actually highlights a few ways engineers fight back against the earth here. If the ground is full of rocks and obstructions, they use rotary bored piling,
Right.
which involves driving a temporary steel casing down the hole first. It acts like a protective sleeve so the walls don't cave in while you drill out the dirt inside it.
Yeah, that sleeve holds the earth back.
Then you lower in a giant steel reinforcement cage, pour the concrete, and finally pull that temporary sleeve back out.
But if the soil is relatively uniform, they use a highly versatile method called CFA, or continuous flight auger.
This mechanism is incredibly clever. It's essentially a giant drill bit, like a massive corkscrew going deep into the earth. But if you just pulled the drill out, the deep walls of the hole would instantly cave in on themselves before you could pour the concrete.
It would completely collapse.
So the auger itself is hollow down the center.
That's the genius of it. As the piling rig slowly withdraws the spinning drill bit, bringing the dirt up the threads, highly pressurized concrete is simultaneously pumped straight down through the hollow stem of the bit.
It fills the void from the bottom up at the exact same rate the earth is removed.
Exactly.
So the hole is never actually empty.
It's a brilliantly elegant balancing act. The pressure of the concrete pushing outward prevents the bore from collapsing.
Here's where it gets really interesting, though, because engineers never just settle for the standard methods.
Oh, never.
When they hit incredibly difficult, unpredictable ground conditions, they start creating these, like, Frankenstein hybrid techniques to force the earth to cooperate, like the Frankie pile.
Ah, yes, the driven and cast in situ pile. This is a fascinating hybrid of the two philosophies we just discussed.
Picture this mechanism. They take a hollow steel tube and drive it into the ground with a hammer, so you get all the benefits of ground compaction without the bore collapsing.
Right.
But then, instead of just pouring wet concrete down the tube, they drop down a really dry, stiff concrete mix. Next, they take a heavy internal weight, a mandrel, and aggressively ram that dry concrete out the open bottom of the tube while slowly pulling the casing up.
And because the concrete is so stiff, the repeated blows from the mandrel force it to expand violently outward into the deep soil.
It creates this massive enlarged bulb of concrete at the base of the pile.
Yeah.
It's exactly like using an expanding wall anchor or a roll plug when you're hanging a heavy shelf in drywall.
That is a great comparison.
The anchor goes in straight and then expands behind the drywall so it can't be pulled out. But they are doing this vertically, 100 feet deep in the earth, permanently locking the base of the concrete column into the surrounding soil.
It acts as an immense physical anchor, dramatically increasing the bearing capacity. And the manipulation of the earth doesn't stop at concrete either.
Oh, right. The stone columns.
Yes, the sources detail aggregate piles, commonly known as stone columns. What if you don't need a rigid pillar, but you just need the soil itself to be stronger?
Okay.
Engineers bore a hole, but instead of concrete, they drop in layers of crushed gravel or aggregate. Then they lower a vibrating probe into the hole to heavily compact that gravel, forcing it sideways.
So they are essentially building a highly dense pillar of rocks that densifies all the loose, granular soil around it, locking the earth tightly together.
Exactly.
But what happens when you aren't even building on land? The engineering article details water crossings. If you need to build bridge abutments over a flowing river, you can't just pour wet concrete into the current.
No, it would just wash away instantly.
Right. Yeah.
This requires total environmental manipulation. They construct what's called a cofferdam. Engineers drive interlocking steel sheet piles directly into the riverbed, forming a tightly sealed box right in the middle of the river.
Just a steel box in the water.
Yeah. Then they drop massive pumps into that box and pump all the water out.
Which creates a perfectly dry, temporary hole right in the middle of the river. But the physics of that are terrifying to think about.
Very terrifying.
You have a hollow box surrounded on all sides by the crushing lateral pressure of thousands of tons of flowing river water just trying to collapse the steel walls.
The internal bracing required to keep a cofferdam from imploding is an engineering marvel in itself. But once it's secure, they bring the piling equipment down into that dry space to install the foundations right into the riverbed.
Wow.
And once the concrete bridge piers are built and cured, they just pull the steel sheets out and the river simply flows around the new concrete.
The scale of the manipulation is just staggering.
It really is. There are other cool methods too, like screw or helical piles that use rotary torque to twist into the earth, and down the hole, hammers for drilling straight into solid rock strata.
Right, but this isn't just a story about giant drills and brute force. To really understand how this happens without a major catastrophe every single day, we have to look at the rule book.
The spec sheet.
Exactly, and that brings us to the actual project specification document, S1.2.
We really have to remember the sheer scale of the equipment performing these tasks. We are talking about track-mounted piling rigs that can weigh up to 180 tons. And their center of gravity is incredibly high because of the massive vertical drilling mast.
Yeah.
You cannot simply park 180 tons of vibrating steel on a muddy, swampy site.
No, and the specification explicitly warns about the ultimate nightmare scenario here, bearing failure.
Yes.
If the surface mud can't support the tracks of the rig, the machine doesn't just get stuck in the mud. It violently shifts its center of gravity, the tracks punch through the crust of the earth, and the entire rig topples over.
A multi-million-dollar machine with a mast dozens of meters long just slamming into the ground,
Yeah.
potentially onto a public street or a neighboring structure. It is a catastrophic failure.
So what does this all mean? It means there's a wild irony hidden in the spec document.
Oh yeah, the platform.
It mandates the creation of a safe working platform before a single drill bit arrives. The contractor literally has to bring in hundreds of tons of crushed demolition rubble or granular fill, spread it across the swampy site, and heavily compact it into a dense engineered layer.
Yep.
They have to design and build a temporary, highly stable mini foundation just to safely park the machine that is going to build the actual foundation.
If we connect this to the bigger picture, it reveals that modern piling is really an exercise in precise logistics and safety administration. The engineering is almost secondary to the risk management.
That's a great point.
The S1.2 document is exhaustive. It details site mobilization, establishing secure water and power, and erecting temporary fencing just to keep the public out of the drop zone.
It even mandates the construction of concrete guide walls in the dirt before board piling can start, just to ensure the massive auger goes into the earth perfectly straight.
Exactly.
And the underground coordination is immense. You're drilling blindly into the earth. The spec requires intense surveying to ensure the rig doesn't accidentally drill straight through existing utility lines, high-voltage cables, or municipal sewage pipes.
Overseeing all of this is the HSE framework. That's health, safety, and environment. The contractor cannot move a single muscle without submitting RAMs, risk assessments, and method statements.
They have to write everything down.
Everything. They have to document exactly how they will execute every single step safely and what their emergency response procedures are if a rig starts to tip or a bore collapses.
The spec even dictates the exact physics of pouring the concrete. If they are pouring into a borehole that has naturally filled with groundwater, they are legally required to use the TREMI method.
The TREMI method is brilliant.
Because if you just dump concrete into a hole full of water, the water will wash all the cement paste away as it falls, leaving you with useless loose gravel at the bottom.
Right, so the TREMI method solves this by using a long steel pipe that goes all the way down to the very bottom of the submerged hole.
Okay.
They pump the concrete straight down the pipe. The wet concrete emerges at the bottom and fills the hole from the bottom up, physically displacing the water and pushing it out the top of the hole.
Oh, wow.
Yeah, so the fresh concrete never actually falls through the water. It stays perfectly mixed.
It's an incredibly smart solution, but it brings us to, I think, the ultimate anxiety of piling.
The testing.
The testing. You've built your engineered rubble platform. You've navigated the massive HSE legal hurdles. You've carefully drilled the hole, used your TREMI pipe, and poured the concrete perfectly. The 180-ton rig finally rolls away, but your concrete column is now buried 50 feet underground.
In the dark.
Exactly. You are about to build a 40-story glass skyscraper on top of this thing, and it is completely invisible to you. How do you actually know it cured correctly?
This raises an important question, right?
Mm-hmm.
How do we trust what we can't see?
Yeah.
We listen to it.
We listen to it.
We listen to it. This is where the testing protocols and the specification become absolutely fascinating. The employer and the engineer do not just take the contractor's word that the concrete is solid. Section 4.7 demands proof through integrity testing.
They require routine physical load tests too, right? Where they actually stack massive calibrated weights on top of a sample pile and leave them there for days just to measure if the pile sinks even a millimeter into the earth.
Yes, the physical tests are crucial, but the acoustic testing is what really stands out here.
Tell me about the acoustic testing.
Oh, the low and high strain integrity testing is pure, brilliant physics. In low-strain integrity testing, an engineer places a highly sensitive motion sensor on the flat top of the exposed concrete pile.
Okay.
Then, they strike the concrete with a specialized handheld hammer. This impact sends a low-strain acoustic stress wave, traveling all the way down the shaft of the pile, deep into the earth.
Like a sonar ping sweeping the ocean floor.
Exactly like sonar. The wave travels down the concrete at a very specific known velocity, the speed of sound through solid concrete.
Right.
When the wave hits the very bottom of the pile, the sudden change in density causes the wave to reflect back up to the sensor on the surface. If the pile is perfectly cast, a solid continuous cylinder, That acoustic wave returns in a highly predictable amount of time.
But what if the bore collapsed slightly while pouring? What if there's a crack or a massive void filled with soil 30 feet down?
That's the beauty of it. If there is a void or a sudden narrowing in the concrete column, the sound wave hits that imperfection and bounces back early.
Ooh!
Yeah. By analyzing the exact timing and amplitude of the returning echo, the engineer's software can essentially draw a structural map of a concrete column that is totally buried in the earth.
That is wild.
If the wave bounces back too soon, they know immediately that the invisible pile is structurally compromised and absolutely cannot bear the load of the skyscraper.
It's an incredible application of physics to solve a blind mechanical problem. And the bureaucratic rigor doesn't stop even after the testing is done either.
No, not at all.
The specification document requires the submission of as-built records like highly accurate topographic surveys proving the exact final geographic coordinates and elevation of every single pile. Only after all of that data is verified can the contractor apply for a taking over certificate.
And even then, they are legally on the hook during the defect notification period. If the building starts to settle improperly months later, the contractor is entirely responsible for remedying the issue before final handover. The level of rigorous, multi-layered verification is really the only reason we can sleep at night in high-rise apartments. We trust the hidden forest because we relentlessly test the hidden forest.
We really do. We have ventured deep into the earth today. We've traced the lineage from 6,000-year-old Swiss river dwellings to modern 180-ton track rigs balancing on crushed rubble.
We've covered a lot of ground, literally.
Literally. We've explored the violent brute force of driving columns into the dirt, the balancing act of hollow augers, the expanding geometry of Franke bulbs, and the sheer logistical mountain of cofferdams holding back rivers.
And we've seen how strict legal and safety frameworks bind all of this raw, chaotic physical power into a predictable, highly managed process. It is essentially a choreographed dance between massive mechanical force and obsessive risk mitigation.
So the next time you are walking past a construction site in the city and you feel that deep, rhythmic rumble vibrating through the soles of your shoes, or you look through the chain link fence and see a giant steel auger pulling a cylinder of dark earth out of the ground, you won't just see noise and dirt.
No, you'll know exactly what's happening.
You'll know exactly the physics of what is happening down there in the dark. You'll know they are carefully planting another concrete tree in that subterranean forest.
You'll see the invisible engineering that holds up the world.
But I want to leave you with a final thought to mull over, something that wasn't explicitly solved in the engineering documents we read, but totally builds on everything we've just explored.
Okay, what is it?
Well, we learned that friction piles hold up massive structures by relying entirely on the lateral grip, the pressure of the dense sand and soil surrounding them, right? We designed these foundations based on the current static state of the Earth. But as global temperatures change, if sea levels rise significantly and coastal groundwater tables shift dramatically upward over the next century, what happens to the friction holding up the millions of piles already resting beneath our coastal cities?
Oh, wow.
If the soil saturates with water in ways engineers simply didn't predict 50 years ago, will the ground literally change its grip?
That is, yeah, it's a sobering geotechnical question for the next generation of engineers to answer.
It really is. Until next time, keep digging.
To download the free PDF file, please click the link in the video description. No email needed. Visit our web shop if you want to buy the Word template for your project.
Thanks for watching. Please subscribe and see next time.